All right, good morning, class. Welcome to a science seminar today. So, good stuff that we have to show you. John Caselli will be talking about these things. He's got degrees in engineering, bachelor's degree from, was it New Jersey?
NJIT, yeah.
Yep, and 2 different master's degrees in engineering. So he has a lot to share with us about how to make buildings high performance with respect to energy. I want to remind you that next week we have an alum returning to talk about computational chemistry, John Pearson. John Pearson? No?
Was going before I came.
Yep, Paul does. Paul remembers John Pearson. Yep. I had John Pearson for organic chemistry. So no.
That was a long time.
That was a long time ago. Yep. John Pearson is a very interesting character. He went off to get a PhD in organic chemistry, dropped out of that, became a high school teacher, then went back again to grad school to get his PhD in computational chemistry because he saw the light there. So, anyway, that'll be next week. You want to come out for that. That should be a really good talk. Maybe not as good as today's talk, but it'll be up there. It's one of the best. So, I don't want to take any more of our speakers' time, but I also want to remind you that if you're interested in these things, for your own home, wherever that home may be, or for Laterno, meet us at lunch. We'll be in the Joyce Room, and you can ask the speaker all kinds of detailed information about where to get solar panels, how to connect it to the grid, all that kind of stuff, right? Bring your notebooks with you, and all those sorts of things, because this is a resource that you won't have with you every day unless you drive out to UT Tyler and visit him over there.
Internet. It's all on the internet.
All on the internet. All right, so let's welcome our speaker.
Do we need to hit record on this?
It's already recorded.
Oh, it's already recording.
Good.
All right. Well, thank you. You'll quickly learn I wasn't born in Texas, but I got here as quick as they could, as they say. Hopefully, the fact that I'm from the Northeast and I speak rapidly will be beneficial because I've got a lot of material I want to try to touch on. It'll kind of be a sampler for you, and then if you want more details about anything during lunch, I'd be happy to try to do that. I'll probably, intentionally, I want to upset you a little bit up front. I want to talk about why we should care about things like photovoltaics and high-performance buildings. And in order to do that, I need to talk a little bit about sustainable development. What is it? What does it mean to the state of Texas? What's the role that buildings play in achieving sustainability? I know there are some faculty who are some interest in building a high-performance LEED accredited building on campus. I may skip over that part if we're running short on time. We can talk to faculty about that, but I will touch on it. I'll show you key elements of buildings, and then again, for those that are interested in the economics, since those of you are interested in photovoltaics, I'll touch on the economics of primarily photovoltaics for you. When we talk about sustainability, it's more important to you and your children than it is to our generation, the baby boomers. I will probably be dead by the time a lot of the problems that I'm going to talk about will truly fully bloom. But in your lifetime, and certainly in the lifetime of your children, this is going to be a profound impact on the way you live and the quality of your life. Probably the best definition of sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And that comes from the Brundtland Commission back in 1987. Put in layman's terms, saving today what we will not otherwise have tomorrow. And of course, there are many, many examples of advanced civilizations that went out of business, in fact, went into extinction because of either, in the case of Easter Island, wood, in the case of the Mayan Empire, water. And so, this is not a new idea that we can use up resources too quickly. During the past 10 years, more than 500 people have moved to Texas every day. And in fact, for the 1 year interval there between 2010 and 2011, more than 1,000 people moved to Texas every day. So more than 500 people a day are moving to Texas. And in fact, we are one of the fastest growing states in the nation in terms of net population gain. And so one of the questions we need to ask ourselves is this sustainable? You're probably aware of the fact that we already have serious water problems in West Texas. It's almost hard to believe that the Rio Grande runs dry, past it, right? so we've already have severe, you know, we're blessed in East Texas. We have a lot of water. We have more water than anybody in Texas, right? 40% of the water for El Paso comes from the Rio Grande. There's already rationing of water. Economic development growth will be limited by water. It's already being throttled by the availability of water. If you look at electricity demand, we are teetering at this point on having the Texas electrical grid, which unlike the rest of the country, there's kind of three major grids. There's a West Coast grid, there's an East Coast grid. Texas has its own grid. And we are now at a kind of a tipping point in terms of having sufficient electricity capacity during the hot summer months and the hot summer days. And so where the grid was, you know, designed to essentially have 1 or 2.5 hour blackouts every summer, you know, you could be experiencing 3 or 4 2.5 hour blackouts every month of the summer. And so, you know, we're starting to see real strains and stresses during what's typically called peak load demand, from noontime to 8 p.m. During hot summer months. Back in my day, we studied a thing called Maslow's hierarchy. You know, it was what's the order of things that we really need to have to survive. Of course, you have to be able to breathe. You need water, you need food, you need energy, you need shelter. I'm just going to touch on some of these and see where we're going. I found this as being an interesting graphic. This is a 2-scale drawing of the Earth as it relates to its atmosphere. The atmosphere of the Earth is like the skin on an apple. I mean, it looks really thick to us, right? But it's literally like the skin on an apple. It's very, very thin. It's very, very fragile. And in fact, we came very close to punching an enormous, probably life-killing hole in that associated with upper atmosphere ozone. And we were luckily able to see, this is an actual NASA photo of the ozone hole when it was at its largest, about the size of North America. And of course it was due to chemical compounds that were actually destroying the upper ozone layer. We caught this and now we're in the process of reversing it. So we are, you know, as humans able to have a global impact on things. I want to touch on this question of carbon dioxide and climate change. You know, the amount of carbon dioxide in our atmosphere has been increasing over time. Why does that matter? You may have heard people talk about the greenhouse effect. You know, part of what you might want to do on your high-tech house when you build it is to have a solar greenhouse. I have one in my home. And how does it work? Well, during the day, the sunlight comes through the glass. It warms up the thermal mass inside the greenhouse. And then you might question, well, why don't you just lose that at night? And the answer is, an engineering answer is very simple. Glass is transparent to visible light frequencies, and it is opaque to long-wave infrared frequencies. And so the heat that you capture during the day does not escape back through the glass at night because of this simple waveband situation. You've heard people talk about the greenhouse effect. Well, what's that got to do with carbon dioxide? Well, what it's got to do with carbon dioxide is transparent to sunlight, and it is opaque to long-wave infrared. And so the more carbon dioxide that you have in the atmosphere, the more heat you capture in the Earth. It's just simple. Is the Earth getting warmer? Yes. The question, of course, that's always debated is that a natural phenomenon or is it a man-made phenomenon? Because you can see every couple 100,000 years, you know, we have these cycles. There's been, you know, 5 times that we know of that the glaciers have completely covered North America and have receded. And so there's a large, you know, cosmic clock, if you will, associated with slight variations in the relationship between the sun and the Earth, dust particles that are in space that attenuate the intensity, you know, all kinds of things, right? I would argue that for us here today, we don't care whether it's a natural cycle or a man-made cycle. We just need to understand that we go through these cycles, and we need to understand to the extent that the burning of fossil fuels is increasing the rate of carbon dioxide in the atmosphere helps to facilitate that cycle, right? You know, when you hear people say, well, the Earth is already warmed up 1.5 degrees Fahrenheit, and it's going to be 3 degrees pretty soon, and it can be bad as 6 degrees, you say to yourself, so what? I'll turn up the air conditioner, right? I mean, I was chief of technology for Carrier Corporation, so that would be a good thing, I guess, right, for business, right? But what's a little more subtle about it is that you have to understand the amount of energy associated with heating up the mass of the Earth by 3 degrees is enormous. And when you have that much more energy in the climate system, it means that our weather becomes much more intense. That's why I don't like global warming. That's why I like climate change, is a better phrase. Our hotter days are going to get hotter. Our colder days are going to get colder. We're going to have more, floods and more droughts. And our weather patterns will be far more intense. Some of the science fiction movies that show these, enormous tornadoes that, make it freezing cold, or, just think about the eye of the planet Jupiter, that big red dot. That's a hurricane that's been raging for hundreds of thousands of years, right? All right. So the more energy in our weather system, the more intense our weather. And we could spend lectures just talking about what those temperature changes mean to crops and pests and viruses and all kinds of things. Our climate is going to change. It always has. How do we adapt to it is really the question. Let's talk about water. Today, 40% of the world's population faces serious water shortages, 66%, 2/3 of the population will face them in less than 10 years. Many of the world's largest rivers are already running dry, including the Colorado and the Rio Grande, and other major rivers around the world. Waterborne diseases fill half of the world's hospital beds. We are blessed with water in North America, and we just absolutely take it for granted, right? We're drawing far more water than we naturally replenish. We're lowering all the aquifers to dangerous levels in North America. Serious water shortages will exist west of the Mississippi. Our consumption rate of water, and this number is not just what you drink and brush your teeth with and shower, it's the amount of water required to sustain our quality of life, to process all the foods that we eat, to manufacture all the clothes that we wear, all the the water that is related to our daily life. And if you compare our 179 gallons a day to half the world's population lives on 25 gallons, and the problems in terms of the Palestine hills are driven by water, right? It takes 4 bottles of water to produce 1 bottle of water, and we're all walking around with these stupid plastic bottles, right? Approximately 870 million people go to sleep hungry every night. Approximately 7.7 million people die from hunger each year. We can't even relate to that, except this way. It's the equivalent of 42 jumbo jets crashing every day. Think about that. If one jumbo jet crashes or disappears in the ocean, it's on the news for a month. If one crashed per week, we'd probably ground a fleet. And I can't even imagine what we would do if 42 were crashing every day. We live in complete oblivion and denial about what's going on around the rest of the world. Well, what's going on? It's about population growth. In 1800, there were 1 billion people in the world. 100 years later, there were 2 billion people. 50 years later, there were 3 billion people. 25 years later, there were 4 billion people. 25 years later, 6. Right? We know what this is. We're engineers, right? Geometric progression. When the population goes up, water consumption goes up, and food consumption goes up, and energy consumption goes up. So here's a little exercise. If you remember anything about this talk, I want you to remember this slide, okay? If the number of water lilies growing in a pond doubles every day, and it takes 100 days for the pond to be completely covered, on what day is the pond only half covered with lilies? Day 99. What's the point? When you've got a problem that grows geometrically, you don't really realize it's a serious problem before it's too late. Right? And the issues in our world associated with water and food and even energy in the great state of Texas are a geometric problem. All right. The other thing I want to point out is that if you take a look at, we're 4.5% of the world's population, we're using 18% of the world's energy. China just surpassed us a couple of years ago. Okay, and they're still climbing. And why are they still climbing? Because this is the amount of kilowatts per year per person, right? And it's still 3 times higher than China. And now look at India, which will be the world's largest population here shortly. They're 17% of the world's population. They're using less than 5%, and they're using, what, 1/12 of the energy per capita that we use. The rest of the world, several hundred million people are coming out of agricultural, rural lifestyles and moving into cities and buying their first automobiles and their first refrigerators and their first air conditioners, and going to be demanding the same kind of quality of life as we have. The developing world is going to drive the train in terms of energy consumption. They already are, shown by this chart. This was the mix, the EIA posts data. This is the most, there's usually a year lag. In 2013, the United States, 82% of our energy consumption was still fossil fuels, right? So as much as we hear a lot about photovoltaics and windmills and all this other great stuff, I think it's wonderful. Understand that, still more than 80% of the energy consumption in the United States is based upon fossil fuels. That's a good thing for Texas. It always has been, right? Solar power, very small percentage still. All right, what's this got to do with buildings? Well, as much as we talk about transportation and fuel mileage, everybody's worried about, how many miles per gallon am I going to get on my vehicle, right? Buildings still consume the majority of the power in this country. I found it ironic when I was at Carrier Corporation. I spent 45 years in industry. I'm really not an academic. When I was at Carrier Corporation, I found it interesting that everybody was running out to buy a Prius, right? I mean, if you want to be green, you drove and it's still, and that's great, right? You buy a Volt, everybody's running out to buy a Prius. You save more carbon with a programmable thermostat. The building sciences industry has done a lousy job in bringing science and education and awareness to people. We consume far more energy in our buildings than we do in our transportation systems. Approximately 70% of the total electricity consumed in the U.S. is consumed by buildings, greater than 40% of the primary power, and so forth in terms of some of the numbers associated with this. There's another set of slides that I use, which is kind of like the lilies in the pond. And it's actually, they're tacked on the end of this, but I'll just tell you what the bottom line is. If we were to quadruple the amount of oil and natural gas that we take out from the earth, quadruple it, right? Instead of us crashing and burning on day 100, we crash and burn on like day 104, right? We cannot drill our way out of the problem of having to transition from fossil fuels to renewable energy. We cannot, I'm Texan now, 15 years. We cannot drill our way out of this problem. We must develop alternatives. I'll die before it's a pressing problem. You won't. Okay? We must have renewable energy. It's kind of interesting if you look at the consumption of energy, that about 2/3 of it is associated with space heating, water heating, air conditioning, and lighting, whether it's commercial or residential. And those are primary candidates for using passive renewable technologies, very much driven by sunlight. All right, so what are the attributes of a building in a sustainable world? Well, it needs to be efficient, energy efficient, and water efficient. It needs to be green, environmentally friendly, it needs to be socially responsible, healthy, and affordable. I was talking earlier, my master's work is in electrical and biomedical engineering, and I wound up, out of a series of things, wind up being, an expert on indoor air quality and indoor air toxins and how it relates to human health. What most people don't realize is there's some horrible little subtleties. While the healthy adult can be just fine breathing a lot of the things that we have to breathe, gases coming off of plastics and all kinds of other things, some of those toxins go interplacenta, and for a pregnant woman and a tiny, tiny little fetus, what is absolutely not a problem at all for an adult can be a serious problem for the unborn child. Sustainable buildings should be able to last a long time. We're still looking at, Roman and Greek buildings and things, big buildings that have lasted for a very long time. We don't build things to last anymore. We build things to be cheap, right? And resilient, which is kind of a newer word, will continue to perform under the toughest conditions. I have two homes, one in upstate New York that's prone to ice storms and blizzards, and one down here that Hurricane Ike decided it wanted to run right over the top of. In both of those places, I've been out of power for 3 weeks. And all of a sudden, the crazy engineer on the block became the hero because my self-generators, that had the lights on and the stereo on where everybody else was in the dark for 3 weeks, wound up moving around the neighborhood to get people's freezers cold again so all their deer meat and everything else wouldn't go bad, right? We need to be resilient. We are so helpless. If you want to see how helpless you are, just turn the water off. When the power was off for 3 weeks in the Woodlands, Texas, people were riding around in really expensive vehicles with wallets full of money and credit cards. But none of the restaurants were open and none of the stores had fresh foods. And Home Depot was operating with a gas-powered generator, and the salesmen were going in with flashlights with one customer at a time so that you get sheets of plywood out, slap them down on the holes in people's roofs. Our society fell apart in a very short amount of time. I find it very interesting that the people that are building houses and putting photovoltaics on them today are not the spotted owl huggers. They're not the liberals. The majority of the people that are doing this are the survivalists because they want to be resilient, right? They want to be independent, right? Here are the real, if we were to look at this kind of technically or professionally, these are the basic attributes of a high-performance building. Energy efficient, water efficient, material efficient, minimize waste, minimize pollutants relative to the outdoors, minimize pollutants relative to the indoors, minimize the physical impact on our outside world. It should be comfortable, it should be healthy, it should be adaptable, it should be automatic. For those of you that are interested in U.S. Green Building Council, you may have seen in the beginning, I am a LEED accredited professional. There's different rating systems. They just updated these in 2014. Building design and construction, interior design and construction, building operations and maintenance, neighborhood development, and homes. And these are typically the major categories that you look at. You look at the location of the building, its location relative to availability of transportation. Is the site sustainable? How do you handle water in terms of not only use, but in terms of runoff? You really want that plot of land to behave the same way it would have before you cleared it. And so forth. The certification levels are certified silver, gold, and platinum, and I'll show you some numbers relative to these. I used to teach when I was in Tyler. I used to teach a high-performance building design course. And there's certain basic elements. The first thing you do is, you worry about the building as it relates to the rest of the world. And very importantly, you worry about the orientation of the building. Back to Greek times, they very much were sensitive to the building and its living spaces relative to the sun. In fact, climate comes from the Greek word klima, which means sun. And so everything was taken into relationship to the sun. There is a right way to orient a building and a wrong way to orient a building. And I'll tell you right now that the houses and buildings that are properly oriented relative to generating photovoltaics, for example, relative to sun angle, are gonna be worth a whole lot more within the next 10 years, something that nobody even thinks about today. The orientation of the roof is gonna all of a sudden be a significant factor in the value of the building. What do we do today? We orient all of our houses to run parallel to the road. Why? Right? It makes no sense. Oh, so the driveway's shorter? I don't know, right? It makes no sense. Those roofs should be oriented relative to the sun. I'll show you. It makes absolutely no sense to have large office buildings have all four sides of the building look the same. The four sides of a big building are essentially seeing four different climates very often. I mean, in terms of the north side versus the south side, the east side versus the west side. It's just these habits that we have fallen into that really make no sense. And the reason we did it is because we've gotten affluent and we've gotten lazy. We're affluent enough to just pay for the air conditioning until there's no power, right? If you design just the basics of a building, just a little smarter, you can save a considerable amount of energy. And then when you add to that some cleverness in terms of passive building systems, ventilation, natural daylighting, the insulation envelope, things like that, you save even more energy. And if you do those two things right, and then you add on top of it the engineering mechanicals that are highly efficient, you can build a building that requires half the energy to begin with. And when you build a building that requires only half the energy to begin with, now it is economically easy to generate the power that you need. It may surprise some of you that are here simply because of photovoltaics to understand that this is not a technological issue. I'm going to show you a picture. Photovoltaics are here today. You plug them in, they work great for 20 or 30 years. There's no technological risk. It works. The only limiter to everybody generating all their electricity today is, first of all, our buildings are highly efficient, and so you need 2 or 3 times the amount of photovoltaics, which leads to the second one: can you afford the upfront cost of purchasing it? If you can get past the first cost, right, what it costs, the check you got to write, right? If you can get past the first cost of photovoltaics, they work just great. And oh, by the way, if you could embed the cost of photovoltaics into a mortgage payment, then in fact the additional cost in your mortgage payment is less than the amount of money you save every month in your electric bill. The economics and the technology of photovoltaics are here today. The single biggest impediment is we have to have more energy efficient buildings. Okay? And we'll talk about that more at lunch for those of you who are interested. Here again are the key elements of high performance buildings. I want to point out that there's a growing trend, and I always believed that it would happen, that by simply improving the operations and maintenance of even existing buildings, you can save an enormous amount of energy and money. If you kind of take a look at it, we're building more and more high-performance, LEED accredited buildings. But if you take a look at the, underneath the data, what you'll see is that the single biggest bang for the buck is renovating existing buildings to making them more efficient. Well, in a histogram, this is kind of what I just said to you verbally. If you look at today's technology and just the way you use it, that's where we're at. If you eliminate conventional systems losses and wastes, you can save 10 or 20% in terms of improvement of energy efficiency. If you build them with a more systems approach, using conventional hardware and maybe just improved sensors and controls, you can save maybe 30%. If you really use a good systems engineering approach with the best-in-class technologies, you can bring that energy consumption down to 50%. And now you can generate enough renewable power to actually have a net zero energy structure. I didn't want to spend a lot of time talking about UT Tyler, but I'll just show you this picture. We have 2 research houses that actually we built, the director of tech's here. We designed these houses and we built these houses. They're full of all kinds of sensors, and you can see there's different kinds of roof patches and everything else. I want to focus on the photovoltaic panel. Right now, this panel is hooked to just one of the houses, the one with the more white roof. It's roughly 600 square feet. It generates 7.4 kilowatts of power. That photovoltaic array, and you can see it's not really large. I mean, you can put it on the roof of your garages or small barn or something. Essentially, a family of 4 can live in that house and will generate 11% more energy than it'll use during the course of a year. Our students, I mean, we put that together. I mean, the company we bought the stuff from, of course, oversaw it, but we actually had our students. We put it together, we plugged it in. It worked fine from day one. It's still working fine. And if you look at, you know, these things are hail resistant. You know, they shoot big BBs at them at high speed and, you know, everything else. Technology is here today. It is not a technological issue. It is not a technological issue. That system costs about $30,000 if you pay for it out of pocket. If you run through the math, the payback if you paid for it cash out of pocket is a little more than 7 years. It turns out that even that is unattractive to most consumers. You know, I mean, if you say to somebody, we can buy this high-performance furnace, you know, high-performance air conditioner, or an even more high-performance air conditioner, and the more high-performance air conditioner costs $3,000 more, and, you know, and the payback is 7 years, very few people are going to buy it. We simply just don't think like that, although, you know, we seem to be quite content to just get 1 or 2% return on our investment in a savings account or something somewhere, right? But if you embed that $30,000, I'm not even talking about rebates right now, if you embed that $30,000 into a mortgage payment, right? And all of a sudden that raises your mortgage payment by like $120 a month, you know darn well your electric bill for a family of 4 is going to be more than $120 a month. So it's not a technical issue, and it's really not an economic issue. For those of you that are interested in developing the next generation of photovoltaics, boy, there's a big window of opportunity there, because they're still only running at like, 12% efficiency or something, right? I mean, just a doubling in the performance of the conversion from sunlight to electricity will change the equation forever, right? Because all of a sudden the economics become a no-brainer. And so, just coming up with the next generation of conversion from sunlight to electricity that's more efficient will make a profound difference. I'll show you some calculations here in a minute. For any building or site, how much area do you have to put PV down? That's another limiter. How much do you need? Right? How much can you afford? And how does the cost of you generating your own electricity compare to the cost of you buying electricity? No matter where you are on the earth, there's certain factors that affect just how much sunlight gets down to you. How much sunlight just gets to the outer edge of our atmosphere is a number that NASA predicts. There, has, and there it is. It varies a little bit, but it's pretty much 1,366 watts per square meter. How much cloud cover you have. What's the conversion efficiency of your PV? What's the angle of the PV relative to the sunlight, right? Cosine theta, right? So if it's perpendicular, it's maximal. There are other energy losses associated with the inverters and things like that. So here's a key number. If you're in East Texas, and I'm assuming that, this area is pretty much just like Tyler, although maybe not with a little more water here, I don't know. But this is not only the kind of the theoretical, but this is also the as measured. We generate about 12 watts per square foot of PV. So there's, if you're going to take home a number, there's one key number for you. You have to understand just a little bit about the trigonometry of the sun. And of course, the sun is lowest in the sky at noontime on December 21st, right, the winter solstice. It's highest in the sky, taking into account daylight savings time, blah, 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 on June 21st. And so, you know, where you are on Earth really kind of defines this geometry, you know. And when you do that, and if you say to yourself, okay, well, the sun is, you know, a little too low in the sky before, say, 9 a.m., and it's setting, you know, and certainly you could do it beyond 3 p.m., certainly in Texas. But, you know, if you were to plot the sun as a function of time of year, if you were standing on your back porch looking south, it kind of creates this windshield, right? This is the envelope of the sun that you can define as a function of where you are in terms of geography. And that tells you whether you got to cut down trees or move the things so you're not being blocked by trees or other buildings or what have you. So that's kind of your passive solar window. And so when you if you design a system and you're going to put in a system and figure out how you want to locate it, you want to have it oriented dead south. And you can actually, you now have these cool little tools you can use to actually, you know, see this. You actually look at this little thing and it shows you kind of everything that's in front of you to kind of see what that envelope is for sunlight. And again, in terms of my designs, I'd probably push it a little bit beyond 3 o'clock, which would bring it down a little bit more on this side, but it's okay. So once you have that, you gotta make a decision. How do you want to orient your photovoltaics? And you've got a couple of options. You know, one rule of thumb is that you have the angle kind of be close to what your latitude is. I would kind of argue, since we use a lot more electricity in the summertime because of air conditioning in Texas, that you would be more inclined to have the optimum angle for your photovoltaics to be more close to maximum during the summer months. And so you really want to push it a little bit more towards the summer solstice. And of course, if you were in the north, now their problem is they don't get as much sunlight as we do, then you'd want to generate more electricity in the wintertime, and so you'd actually want to tip it down some, so that cosine theta was more favorable in the winter months. I know I'm whistling through all this, but again, we can talk about it more later. Here's the simple way that you would calculate how much PV can you generate, how much electricity you can generate. There is a theoretical maximum. You have to then add in some cloud cover factor. You've got this cosine angle thing relative to your PV, what the efficiency of the hardware is, and so forth. And if you kind of do the math, there's a pretty wide range. As you can see, there's a range of these numbers. So the upper end, you know, would be something like this, right? Maximum would be 30 watts per foot squared, theoretical maximum. And if you kind of do the math for the Texair houses and the Texair hardware, it came in at 11.6 in terms of the theoretical calculation, and we're actually measuring about 12. So it's a very simple calculation. You got to make some assumptions. Probably the toughest one would be kind of cloud cover, maybe, because the other things you actually can control as an engineer. So that's kind of the simple calculation. Let's talk a little bit about the economics. Another takeaway number, kind of rule of thumb, that panel that you saw was about 600 square feet. That panel will generate about 15,000 kilowatt hours per year. Okay, so for a residential structure, that's great. And then also, if you're going to build a bigger system, like for buildings, you know, on roofs or buildings like this, then that's, you know, you can scale that up. The installed cost keeps dropping because the hardware side of it has been dropping. Today, the installed cost, materials and labor, about $2.75, say roughly $3 per watt. And of course, for large installations, because now you got economies of scale, everything else, it can be $1 less. Until there's a significant technology step function, you can't compress it a whole lot more simply because the labor component. You know, we've been bringing the hardware cost side down, but there's still that people have got to get up there and, you know, got to install it. Okay, for those of you that are interested in in LEED, there was an expression of interest in terms of like, does it cost a whole lot more, and what do you save, and all this other stuff. If you build a LEED certified building, your design costs are gonna be higher. Why? Because you do a lot more concurrent engineering upfront. You do more engineering upfront. You have design charrettes, you have do a bunch of things that you would not normally do in regular construction early on. And so you've got a design cost increase. You can actually build a building for no additional cost. I mean, there's a lot of buildings that are LEED certified or LEED silver that came in at a per square foot construction cost that's equivalent to a non-LEED building. There are documentation costs because you've got to certify all the materials. There's a lot of paperwork. There's no question about it. And my home is probably LEED platinum, but I'll be damned if I'm going to, go through the trouble of proving it to somebody else. I quite frankly don't care. Right? Okay. For academic buildings, total project costs are influenced in terms by a much wider range of motivations. Right? If it's a commercial building, then how much you could rent it for, how it appreciates, what its resale value, those are pretty simple metrics. But a lot of academic buildings are constructed to make a social statement for ego, whatever, right? By God, we're going to have a platinum building, and they put all the kinds of crazy, wind turbines and stuff on it because it's an experiment for the students and everything else. So it's kind of hard because there's a much wider range of costs per square foot in academic buildings than there are in residential or regular commercial buildings, and you can see that by these numbers. The actual per square foot cost for academic buildings that are either LEED certified or silver can range from $175 per square foot to $375 per square foot. How about the savings on after you cut the ribbon? As you would expect to have significant reduced operating costs. And so you will see reduced energy costs on the order of 25 to 30%, 19 to 30% for water, depending on where you are and how much rainfall you get, with pretty much an aggregate reduced annual operating cost of 20%. So take away for those of you who are thinking about LEED certified buildings is that 20% number.
Look at that, higher test scores for students.
Absolutely. Yeah, so I'll comment on that in a minute. So productivity, fast reader, productivity improvements, daylighting, profound difference. There's been studies where, places like Walmart puts in skylights, and the sales in the stores with skylights are 15% higher than the sales in stores with artificial lighting. I mean, there's a lot of really interesting, studies. Outside views, people heal faster and get out of the hospital 2 to 3 days quicker if they've got a nice outside view from their hospital bed. There's thousands of those studies, right? Improved indoor quality and ventilation in terms of actual productivity, mental function, recall, that sort of thing. So to your comment. In Asia, where test scores are, and competition is so critically important, anything you can do to improve test scores is really looked upon very favorably. And there are a lot of studies. The numbers vary widely, but it's not uncommon to see a study that shows that students are scoring 15 to 19% higher on test scores when you've got a building that has good indoor environmental quality and daylighting, views. Increased employee recruitment and retention, lower sick leave, lower absenteeism, easier to hire people, less people leave. And you kind of add up some of these slightly more qualitative things, and again, the magic's in the math, right? But I stepped back and look at all, because I used to do this, so try not to over-exaggerate or understate. But really, these intangibles add up to be equivalent to about 80% of the occupancy cost for a building, just in terms of these reductions in costs associated with sick leave and absenteeism and replacing people that leave and that sort of thing. you know, this audience, at least if we're talking about an academic building, isn't going to care about some of these things, but the numbers really are quite remarkable. You know, green buildings have much lower occupancy rates, higher rental rates, returns on investment are excellent. You know, the values, I mean, all the measurements of a commercial building that people would care if they're investing money in a commercial building are very, very favorable. And, you know, the operating costs are significantly lower. The savings are a little bit smaller simply because these things are very energy intense. You can picture, you know, in a commercial building where you've got, you know, everybody's got at least one computer, and you know, there's lots of things going on that are consuming electricity that just has nothing to do with the structure. Show you a couple neat buildings. This is the Rand Corporation building. Lots of emphasis on its orientation and its shape. This was LEED Gold. I'm actually familiar with this site in Pittsburgh. It was an old brownfield train yard. It was just a mess, and they built this structure. You know, it can be a small building. This happens to be a little credit union building. And you can see some of the things that they do, right? High efficiency HVAC, rainwater capture, porous concrete to reduce runoff, native plants. You know, nowadays it's more you know, we're using more and more LEDs. A lot of renewable energy, low VOC, organic compound, paints and flooring finishes, that sort of thing. Here's a school. Came in $2 million under budget, saves $50,000 a year in operating expenses. A lot of daylighting, right? So for academic structures, daylighting and views are very important. You can pretty much get all your domestic hot water that way. Operable windows for natural ventilation, and so forth. You know, you know yourself in Texas. Texas is interesting. We've got what are called shoulder months, right? You wake up in the morning, you got to turn the heat on, and by noontime you got the air conditioner on, right? You know. You know, intelligent use of natural ventilation. I can't tell you how many times, you know, I'm freezing in the house and I go outside, it's nice and warm, right? You know, it's warmer outside, and vice versa, right? It's cold, you know. So if this is the way I used to say it when I was in industry. We have the technology today to build buildings that are smart enough to know when to breathe in and out and when to hold their breath. Humanize it, right? We have in sensors and controls and servos and everything else. We can build buildings that are smart enough to know when to breathe in and out and when to hold their breath. All right, I'm just going to quickly show you what's down the road here because we're running out of time. So this is the Texas Allergy, Indoor Environment and Energy Institute. It was created in 2007 at UT Tyler with a grant from the Emerging Technology Fund. We've gotten money from lots of different folks. We've funded a lot of faculty and a lot of students doing research in those structures. I'm sure if there are students interested in utilizing some of that space for particular projects, we'd work that deal out, right? Because we're kind of just down the road. This is what the houses look like. We intentionally designed them and built them to look like normal houses, right? It makes no sense to build something that looks like George Jetson should be living in. Who's going to buy it, right? So we did these things to look, you know, absolutely normal. This, you know, one of the houses we built to be kind of the best commercial practices kind of thing. It's 50% more efficient than the average house in the United States. It comes in at about $90 a square foot. And the Patriot House is the one that the PV is hooked to. It's got some little additional neat technology, including geothermal wells and blah, blah, blah. And this generates 11% more electricity and still comes in at a very reasonable price. Some of the things that we're playing with, I guess, you know what I'd rather do? I'd rather kind of open it maybe to a couple questions rather than go whistling through this. So anyway, that's kind of it in a quick nutshell. And again, I'll be around at lunchtime if there are any questions I can specifically
See
answer.
if we can get a couple of questions in before we break for lunch. Questions from the audience? Yes.
As far as like putting solar panels on the roof and stuff like that, when you see in the backyard, are they like completely stationary for the entire year? Or do you have those
Okay, that's a great question. There's actually a company in Tyler that have a tracker, a sun tracker, right? So it's a big panel, and it actually tracks the sun to keep it optimized. You get, I'll see if I can answer it quickly this way. It's a little more efficient because they have cosine theta, right, the tracking. But the additional cost and the maintenance of the actual tracker is such that I think it's actually easier to put slightly more fixed panels than it is to go through the active tracking, right? Now, the difference would be is if you're space limited, right? Because you just don't have the acreage, right, for the additional panels, and so you're forced to do something like that. But kind of my personal feeling is, it's just easier to put more fixed panels on.
Okay, one more question before we break for lunch.
What about the net energy equation for photovoltaics? Last time I saw that it took around 15 years for them to break even in terms of the energy that it took to refine the silicon, produce the photovoltaic panel, and then versus the next.
So you mean if you include the manufacturing of the PV as well? Yeah, because it takes a lot of energy to turn sand into glass. So
Yeah, yeah,
no question about that.
okay.
So, you'd want to do something, as we go more and more to this, you're going to want to use renewable energy to yeah, absolutely.
Okay, if you have more questions, you can come down and talk to our speaker. Otherwise, we'll be meeting in the Joyce Room of the Corner Cafe. In a few minutes, please join us there for more questions. Let's thank our speaker.
I got through it.
Yeah, we did. We did good. That was a great talk.